All right. Welcome to our last talk before the lightning talks this afternoon. So here we've got Adam Harvey from New Relic, and the talk is called 4-ish non-cryptographic hash functions enter, one leaves. Please welcome him.
Thank you for the round of applause before. That always helps. I am indeed Adam Harvey. I am from New Relic. This talk has literally nothing to do with New Relic, so that will be the last time I mention that. So what I'm here to talk about is non-cryptographic hashing. So for those of you who were just in this room, of course, there was a wonderful talk about cryptography. This is kind of the flip side. This is for all the times where you don't really care about security or verifiability or protection from attacks. So, fundamentally, let's start with a few definitions. I'm sure most of you know what a hash function is, but just to make sure we're on the same page and to ease gently into the talk. A hash function takes an arbitrary amount of data and breaks. That's always good. My apologies. One moment, please. Oh, that is interesting. Okay, well, let's see how we go. The animations are going to be fairly uninspiring then because they're not working. Okay. Basically though, a hash function is something that takes an arbitrary amount of data and turns it into a finite amount of data. The finite amount of data is of course usually an integer, and we are all generally fairly familiar with this concept courtesy of the various cryptographic hash functions that we use and take for granted. For example, we have MD5 SHA-1, SHA-256, SHA-512, and of course these all work basically that way. You give them a binary string, stuff happens in hashlib, and out the other end you get a number, basically. Now that number might be encoded as a hex string, but you get a number. And of course we use these every day, whether directly or not. They underpin SSL, encryption, password storage, checksumming, and a lot of other things that we take for granted. So those are cryptographic hash functions. Now, cryptographic hash functions have specific qualities. They're designed to be as difficult as possible to generate collisions, and you shouldn't be able to easily work back to figure out what the input was. You then also have another category of key derivation functions, which are usually built on top of these hashing functions. And these are used for passwords. You know, you're trying to make it as hard as possible for somebody to be able to generate a rainbow table. So, if that's a cryptographic hash function, I guess it stands to reason a non-cryptographic hash function is everything else. There's also a place for functions that basically just, you give them some data and out the other end you get a number. And it doesn't really matter whether it's easy to reverse back to the original data. It doesn't really matter to some extent how well distributed it is. And of course you want it to be fast. This is the world of the non-cryptographic hash. Now, that all sounds great in theory, but why would I want this? Why does it matter? Well, there are a number of uses. You might want to track things that you've previously seen. Now, of course, in Python you have a set type, so in theory, this is unnecessary, but if what you're tracking is large data sets, maybe genetics data, something like that, and you just want to know if you've seen it before, you don't want to keep the whole thing in a set because your memory usage is going to just skyrocket. Instead, you just want to keep a number that represents that. Now you can use hashlib for this, but you might want to minimize that. I mean, even the smallest hash function that hashlib provides is, I think, 64 bits of output. A lot of non-cryptographic hash functions can give you 32 bits. They can give you less if you really want to. It's a very quick way, particularly in scenarios where maybe you're not too concerned about 100% accuracy, but you want 99.99% accuracy of tracking what you've already seen. Another option is you might want to check if something's valid. You can use these as checksums. Most of these were originally checksum functions in the first place. I mean, a checksum really is just a non-cryptographic hash, right? So there are scenarios where you might just want the 2015 version of a parity bit. In those situations, these will get you there. Interopt's a big one. Actually, I said I wasn't going to mention New Relic again, and if anybody from New Relic sees the video, skip the next 60 seconds or so. We implemented a feature last year which required us to be able to track what URLs people had basically visited. In order to do this, we needed some way of basically having a reference back, and we ended up using a non-cryptographic hash function because people spec weird things. People get clever ideas and then they get written down in specs, and whether they're a good idea or not, it wasn't. You then have to implement and deal with them anyway. So maybe you're just going to have to know how to implement FNV1A. Finally, maybe it's fun. Like, you know, there's some maths here. It's kind of nifty. Some of these are really simple. You know, it's a chance to do something a little bit different and maybe push Python in ways that you don't usually tend to push it. All right, how are we going to implement these functions? Well, let's set some goals. We probably want it to be fast, and we probably want the output to be reasonably well distributed. Now, the distribution one's an interesting thing because in a lot of cases, the reason why you care about the distribution of the hash function is because a lot of the time you're implementing a hash table. Now, this applies more to people who are working in C, C++, not even really C++, I guess it's just C nowadays. Now, in Python, if you're implementing a hash table, chances are something has gone horribly wrong with your life. But on the off chance you actually need to, this is another goal that you would have. You also just don't want clumps in your output. I mean, you don't want things to be bucketed the same if you're going to do this, because that leads to collisions and that leads to getting false positives or false negatives, depending on what you're doing. So, one of the things that you need to distribute the output is the avalanche effect. The avalanche effect basically is just a fancy way of saying, if I have these numbers and they only differ in these bits, we don't really just want variance to be there, because that basically means that there's not very many options for what can come out the other end. You want each change to your data to have a bigger effect on the output. You want to affect all of these bits. So probably the biggest thing that you will see in the implementation of a hash function is basically coming up with a way to distribute the output over the entire number that you're generating, whether it's 8 bits or 32 bits or 128 bits or whatever. Now, hash functions in general work basically this way. I mean, this really is the gist of the talk. You can just, this is the TLDR. You can pretty much leave after this. Python, of course, being Python, probably provides a cleverness function in the standard library if you figure out what to import from. Chunk sizes can vary. Some of them are 1 byte, some of them are 4 bytes, but that's pretty much how it happens. This cleverness thing is actually what's called a mixing function. So if you ever see the words mixing function on a Wikipedia page, this is what it refers to. You can now drop it into conversation, and it's awesome. People will look at you very funny if you drop it into conversation. Basically, all a hash function does fundamentally is you have a rolling hash value. Think of it as a context if you like, but it's really just a number usually. You have a block of input data, a chunk of input data, however you want to call it. You will mix those, hence the name, and then you will generate another number out the other end. Now, you might have some pre and post processing depending on the function, but that's really all that matters. How do you implement this cleverness? Well, in general, you do it with unsigned fixed length integers. You use bitwise operations heavily. You do some multiplication, and usually there is at least one magic number that is a prime number. So let's just go into that a little bit more. Now, integers. Now, Python has this wonderful quality where it will auto-promote integers. Integers are arbitrary precision. If you want to deal with 1,000,000 digits, you can deal with 1,000,000 digits. However, almost every hash function in existence, at least all the ones I know of, rely on integer overflow behavior. If you have a 32-bit integer and it's 2 to the power of 32 minus 1, and you add 1 to it, you need to get 0 out the other end. So, how do you do this in Python? Well, for the purposes of this talk, I've used NumPy in all my examples because it provides this convenient uint32 object. This supports the semantics we need, kind of. There is, however, another problem. The moment you mix in a normal Python integer and do any operation on a uint32 with it, you still get a numpy type out the other end, but it will auto-promote because it's trying to be helpful. It's actually trying to do the right thing. So you're going to see some really ugly code. There is going to be an awful lot of uint32 constructors. You may just have to deal with it. I would suggest actually if you're going to implement a lot of these, just alias it to I don't know, I or something. You'll probably feel better. The other thing I touched on was primes. Most hashing algorithms in general include at least one, often more than one prime number as a constant. This is mostly so that you distribute more evenly across buckets. If you have, buckets are usually, in hash table implementations, buckets are usually a power of 2. You know, you might have 128 buckets, you might have 256. If you accidentally have the same prime factorization of your buckets as you do for some of the constants that you're using to manipulate the state of the hash function, you can end up inadvertently bucketing everything into the same thing. And we're actually going to see an example of that a little bit later on. So let's walk through an example. FNV1A is a venerable hash function at this point. It's 24 years old. It was created by Glenn Fowler, Landon Kurt-Knoll, and Fong Vo in 1991. It's been improved a couple of times since. It's still in wide use today, and one of the reasons why it's in wide use today is that that's the entirety of the implementation. It's a very, very simple hash function. You can implement it in any language you want to. You can probably do this in the language that I'm not going to name because it's a code of conduct violation. You can probably also do it in intercal. There are a lot of ugly uint32 calls, as I previously threatened, but conceptually it's very simple. It's a byte-wise algorithm, most of the older ones are, and then you exclusive OR it with the existing hash, and then you multiply it by a magic number. So, we can actually walk through this. That shouldn't have wrapped. Okay, so first we set our hash value to a number that's actually specified as part of FNV1A. Having just gone on about how primes are important, this actually isn't a prime, in spite of the fact that you probably would believe it was if I told you it was. It's simply a non-zero value because the first version of FNV was called FNV0 and its initial value was 0, and it turned out this did bad things. The offset is actually the FNV0 hash of the email signature of one of the creators. Cute. So, if we're going to call it with the binary string AB, let's walk through what happens. So, this is what hash has been set to. We now have the first byte, which is lowercase a. We'll assume this is ASCII or an ASCII-like encoding, so it's 97. That's the binary representation at the bottom. Then we do the exclusive OR. Only 3 bits change. So remember that avalanche effect thing I just said earlier? That didn't work. But that's why the multiplier is there, because all of a sudden we change a lot of bits. Now, those of you who have unfortunately also got computer science degrees will probably have noticed that that is very close to 2 to the 24. It's actually the closest prime to 2 to the 24, I believe. That is there because it gives you basically bit shifting behavior as well. Now, FNV1A kind of hides the bit shift in here, but every other hashing algorithm we'll look at uses bit shifts heavily to get this avalanche behavior. So what this is doing is it's going to shift everything, and then it's going to add some noise basically at the lower end of the number. If we look at B, so the next byte is only 2 bits different. There's a 0 that you can't quite see at the other end. So it's 98. Now once again, when we multiply, only 3 bits get changed. Oh, sorry, exclusive OR, only 3 bits change. But again, we do a multiply, and this time you can see how well distributed it is, even after only 2 very similar bytes. Every nibble has 1 or 2 bits that have been changed. So we're already seeing a real avalanche behavior here. Things are getting moved, things are getting mutated. It's all pretty cool. So now we know what a non-cryptographic hash function is, what it looks like, what it tends to do, and what you can use them for. Let's look at a few functions. I'm going to look at the 32-bit versions of them. A lot of these functions have 64 and 128-bit versions as well, but for simplicity, let's just keep it to 32 bits. I've chosen functions that are considered to be reasonably state-of-the-art and are also, I think, feasible to implement in Python. There are some hashing functions out there like city hash and farm hash that are extremely cool and complicated and basically rely very heavily on x86 64 assembly. I don't even want to know how you actually do that in Python. So we need to figure out how we're going to compare them. Now, if we remember the goals earlier, we want them to be fast and we want the output to be well distributed. So how do we judge that? Fast is easy. We just look at CPU time and that gives us a pretty good idea. Particularly if we, and for the purposes of benchmarking, we'll load all the data into memory before we deal with it, so it gets rid of any I/O overhead. We also want to look at how well distributed the values are too. Now, the easiest way to do this and the most numerical way is to look at the number of collisions. So if you have 200,000 input values and you have 199,999 output values, then you had a collision. It's pretty basic subtraction. So we can use that to quantify, because I love quantifying things. We can use that to quantify how good each function is. I've used two input sets. The user share dict words list that comes with macOS, because I did the first testing of this on macOS, and a file which contains nothing but the numbers 0 to 235,885. The reason why I chose that number is because that's the length of the words file, so it means we have the same number of inputs to each of them. Now the words file, as you'd expect, is mostly letters, some uppercase, some lowercase. There's a little bit of punctuation in there, just hyphens and stuff, but it's pretty straightforward. The numbers file is in many respects a more interesting test because it's only ever going to have 10 values, 0 to 9. So it's a very good way of testing whether the bucketing behavior is actually resilient in these functions. Since we've already looked at FNV1A and we already know how it works, let's look at the results. So for the numbers, you can see it ran in 1.63 seconds. I mean, the actual absolute numbers don't really matter here. It's really just the relative state. The words has more data, so it took longer. There were no collisions on the numbers. There were 5 collisions out of 235,000, whatever it was, entries on the words. That doesn't sound great, but if you're aware of the birthday paradox, which is basically that if you have a room full of like 20 people, there's a 50% chance, roughly, that 2 of them will have the same birthday. The same principle works here. For a naive hash function generating 32 bits of output with 200,000 inputs, there is a greater than 75% chance that you'll have a collision. So that's actually really about average. Another way to look at the distribution, and it looks like noise, and you'll see better examples later. And I need to credit someone. I shamelessly stole this from a Stack Exchange answer by Ian Boyd. So Ian Boyd, if you ever see this, I'm really sorry. Basically, the coloured bits are where values got put, and then the white pixels are values that were unused. So in a perfect random hashing function, you would expect to see complete noise, basically. We see basically noise. I realise for those of you at the back, this is probably very difficult, but just take my word for it. Okay, next up is murmurhash 3. What happened to my styles? This is very sad. Murmurhash 3 is a little bit bigger, but let's break it down because it's not really that hard. Remember the principles. You have a mixing function, you might have an initial state, and you have an end state. And the mixing function only takes 2 inputs, a chunk of data and the existing hash. So to start with, we seed it. There are some constants, actually quite a few constants. I am sure some of those are primes. I actually don't off the top of my head know which ones are, except that one definitely isn't. See, computer science degree. And there's also a seed, which maybe you'll set yourself, maybe you'll just hard code a value. A lot of these functions take seeds. It's not terribly important to choose one very carefully. It's just something. It also means that if you need to generate different hash values for different users, then you have a way to do it. So then we start the mixing function. We grab some data. Murmurhash operates 4 bytes at a time rather than 1 byte. But of course, we may have less than 4 bytes at the end, so we still have to check that. We use unpack. Funny story, I became aware today that the int class in Python 3 now has a from bytes method. It is actually slower than unpack, even though unpack has to scan a format string. So, don't know, weird. otherwise, this looks pretty similar to what we expect. We have some data coming in, we multiply it, we do some bit shifting just to try and get some more randomness. Not randomness, I'm using randomness the wrong way. Try and get some values more evenly distributed across the hash. Do another multiply, exclusive OR, more stuff, and it gets mutated. If there are less than 4 bytes remaining, then there's an alternative mixing function. And this is important if you are writing a hash function that works on more than a byte at a time. You have to have some way of actually mixing the remaining bytes, otherwise you've just thrown away entropy. Pretty much the same thing. Bit shift, bit shift, bit shifts, some multiplies, some exclusive ORs, and you end up with a hash value. Finally, at the end, and this is something that's very fashionable at the moment, you have a series of post-processing steps to try and introduce some more pseudo-randomness into the whole thing. So it's, again, the same sort of thing. The difference is that the inputs, instead of coming from the data, are hard-coded constants, which have presumably been chosen to maximize the distribution of the values that come out the other end. So murmur-hash 3 is quite a bit slower. The reason it's quite a bit slower than FNV1A is a mixture of reasons. Firstly, we have to unpack the four bytes at a time. Secondly, it does a lot more. I mean, FNV1A was basically an exclusive OR, a multiply. That was it, wasn't it? So this obviously does a lot more. CPython is an excellent piece of engineering, but if you want sheer mathematical speed, it's not necessarily your best friend. It also generates 5 collisions for each of them, which, as I said before, is kind of about right. And the distribution is, again, pretty noisy. Another relatively new hash function is xxhash, which has been adopted by a number of projects, including FPSense and TeamViewer. They're very keen to tell you that on the website, but I don't know what they're actually used for. Has a similar construction to murmur-hash, but it reads 16 bytes at once and is, I would say, about as long as you would feasibly actually want to implement something in Python. I'm not going to go through all the boilerplate. There is pre-processing at the start. There are some constants. The interesting thing is it reads 16 bytes at a time. So this is the mixing function for each 16-byte chunk. And it keeps separate accumulators in the hash, and only at the very end of the read, after it's read all the 16-byte chunks, does it actually combine them. Again, I should have actually put ROTL on there, I'm sorry. It's a left shift and a right shift. Again, at the end, it's basically shifts, exclusive ORs, multiplications. Same parts, just put together differently. It's like cooking. You really only have like 10 techniques and 100 ingredients, but think about the variety of dishes out there. Again, you have separate mixing functions for 4 bytes at a time and for 1 byte at a time. So when you come to the end of your data, everything still gets taken into account. Again, lots of post-processing. It's quicker than murmur-hash in Python. And the reason it's quicker, I'm pretty sure, is because it's just hitting the cache better. It's reading 16 bytes at a time. It's doing more stuff with stuff that's in the CPU cache. You get basically better performance. Has a slightly worrying number of collisions on words, but that's okay. The distribution in general, again, looks pretty noisy. So these are all good hash functions. Let's look at one that's less good. This is super fast hash. The name alone kind of worries you. I don't expect you to read this. I will, however, note, because I don't think I put it on the next slide, there's no initial state besides the seed and the length of the data. There are no magic constants here. The mixing function, actually it reads 4 bytes at a time but unpacks them into short integers and then mixes them in an interesting way. There are some gymnastics around bit shifting, but if you kind of pay attention, the offsets are pretty much the same every time. And then at the end, there is a lot of post-processing, and it's all bit shifts and exclusive ORs. The reason for this, I'm reasonably sure, and smarter people than me have also said this online, so I assume it's probably actually true, is that the mixing function doesn't do a very good job, particularly with small inputs. It can collapse into the same set of states based on the first 16 bytes on an overly common basis. Now, remember how I said earlier that numbers doesn't have a lot of entropy? It's only got 10 digits. Well, That's the net result. A lot of them collapse into the same states. So you end up with 10% of your input basically ending up as the same thing. Words does a little bit better. I don't know how obvious this will be. Those of you at the front might actually be able to spot this. It looks pretty noisy, but there's a big stripe up the right-hand side here. And what that means is that this is where the values are collapsing into. So this is for the numbers data set. Way too many of them are collapsing in here. In actual fact, it would be much more dramatic, but I actually tweaked the script I wrote to generate this to actually still have some color in the rest of it. That's not very good. It could be worse, to be fair. This is the ungoogleable JS hash. I'm not going to show you the implementation of this. It was invented by a guy called Justin Sobel. I'm only aware of it because we used it at New Relic in the product I work on until 6 months ago, when we got some fairly interesting bug reports about very bad behavior related to hash tables in our library, and that's why. Finally, let's look at CRC32. CRCs are a very old set of functions. They rely on polynomial division to generate a checksum. Checksums are basically just hash values. There are really serious maths here. It's late in the afternoon. I don't think any of us are ready for this, but here's the implementation. So, why wouldn't you use this all the time? Well, actually you might. It's not that bad. There are 8 collisions, 0 for the numbers. It's obviously way faster than everything else. It's like a third of the time of FNV, which is the previous best. The word collisions are potentially an issue, so it's something you would have to be aware of. Depending on what type of input you give it, you may get a few more collisions than the state of the art. The other problem with CRC32 is it uses a lookup table very heavily to actually do its division. Now, on this laptop and this phone and pretty much everything in this room, we're probably fine. If any of you went to the $7 Python computer talk earlier though, maybe not the thing to choose. So, in conclusion, you need to know your environment. If you're implementing things in not Python, I mean, I realize this is Pycon, this is a very crazy statement, but maybe you're doing something in C. Murmur hash and XX hash suddenly become way faster. And the reason they become way faster is because they exploit very specific features of modern CPUs when you write the code in C rather than idiomatic Python. They use cache locality, they use read alignment, they do a lot of things to their advantage. Now in Python, the problem is that's all overhead. It all still has to go through CPython, so you pretty much lose every single advantage, even if you're using the right assembly instructions. So in Python, the byte at a time approach is actually faster because of the way the bytes arrays are represented internally. You need to know your requirements. Understand how many collisions you're willing to bear. There are probably uses where being right 98% of the time are fine. There are probably places where 90% of the time is fine and you can use super fast hash and paint little decals on your computer. And if you can deal with a few more collisions and you're writing in Python, then you can just use CRC32 because you should also respect the standard library. Python only provides 2 non-cryptographic hashing functions and they're both out of zlib, Adler32 and CRC32. If you don't need the closest thing to perfect hashing in the world, you just need good enough hashing, then CRC32 is there for free. You don't have to do a thing. All you have to do is import zlib. Thank you very much. I believe I have about 10 seconds. I'm happy to take very rapid questions, which will get very rapid answers, most of which involving me not knowing. Yo. Have I come across Jenkins hash? I'm sorry. Have I come across Jenkins hash? I know the name, I haven't looked into it in any detail. I have looked into a number of hashes beyond what was in this presentation, but not that one specifically, I'm sorry. Yep. Sorry? Aliyah. No, that one doesn't ring a bell. There are, I will just note actually, there are a lot out there. There's like a cottage industry of people, and for some reason it's on Google Code instead of GitHub. There's like a cottage industry of people out there who just as a hobby come up with new non-cryptographic hashes, which is great because you get some really good ones out of it. You do also get some less good ones out of it. Sorry, super fast hash. Yep.
Hi, so when you were talking about hashes that are for set existence, So I think, were you referring to the Bloom filter?
Yeah. So that's a really good example of somewhere where this is really useful. So Bloom filters, for people who aren't aware of them, basically are a very good way of compacting a set of data down to look for basically positives, as long as you accept that there will be a certain false positive rate. It's either false positives or false negatives. I'm hoping you can tell me which one. So yes, this is one area where they're very useful, because this can crunch down the amount of data that you actually have to put into your Bloom filter and therefore carry around.
Yeah, so it doesn't give any false negatives. It only gives false positives. And the thing is this, that basically in your experience, have you so Bloom filters are fine, because I think that from a collection containing millions of items, 10 million items, so your computed Bloom filter is around 120, 130 KB, which is really nothing, because if you store all of the pointers, that would still like go into the hundreds of MBs maybe. So the thing is this, that have you seen any, because if you were to implement this for a list of containers containing a lot of collections, then other than suspending everything inside memory, I'm not really sure about how to do it. Is there any open source solution that
there probably is that I'm unaware of in Python? You can certainly, the beauty of Bloom filters is you can pre-compute your filters. So I mean, this is something that you would do before you ship your software, basically. Like, maybe I'm misunderstanding the question.
Yeah, so my question is that I work at, I have a startup, and we've got a lot of songs, right?
Yep.
So we've got a lot of songs, and if we scale up to Spotify proportions or something like that, we might have 1 million songs, right? Then we have a lot of different users. So if we have 1 million users and 1 million songs, the Bloom filter that would have to be attached to each song would be 130 KB big. And multiplying that by 100 and suspending that in RAM might be a little expensive.
Yeah, I mean, that might be one where you can use a completely different technique like audio fingerprinting or something like that, and then use those to generate your Bloom filter. So have an additional processing step on the way in.
Okay.
I think we are pretty solidly out of time, because we've got lightning talks in like 5 minutes. So thank you very much. It's been great.